Hello everyone, my name is Teja and I'm gonna today talk about online recommendations personalized to user behaviors. So this is in the context of personalization, which is a big phenomena that's been disrupting digital technologies in the past couple of decades, starting from the very famous Netflix fries problem to targeted advertising that you see in many different channels these days. I think personalization has a very far-reaching uh, impact on technological changes that we will observe in many business practices today as well as in the future. And so that's the very broad context for today's talk. And today we're going to look at really how do we personalize in a feedback loop. So there's a closed loop between a firm which is interacting with customers, and the firm is going to really aggregate feedback and really improve its offerings or its ads or recommendations in a closed loop fashion. Okay, so that's the personalization aspect that I'm going to try to get to today. And without ado, so let me talk about recommendation systems. So recommendation systems are a core part of many different commercial offerings. As I mentioned, Netflix. There's also offerings like YouTube, Spotify, the newsletters that you see from various organizations and firms, app notifications. They all have some sort of a uh, uh, information that the firms want to reach out to you so that you discover new things that you haven't seen before, and so on. Okay, and they're very critical for success of many of these firms in terms of engagement with their users. Okay, and there are many solutions for recommendation systems in the literature, both in academic literature as well as in practice. Here's a simple URL and captures some of these systems. And one of the core ideas that drives the effectiveness of recommendation systems is the idea of relevance. And it's naturally is impacted by many different factors. Here I've listed a few factors like the cold start problem. Um, the cold start problem. It also is impacted by how well you model your users. So, for example, if your user demographic is the older generation versus if it's the student population, the way you think users behave influences your design and therefore also influences what is relevant ads or recommendations that you serve. There's also other things like diversity, sparsity, timeliness of the recommendation, and so on. Okay. So here's an example, and we kind of will rely on this example for at least for the first half of this talk, which is a screenshot of YouTube, and you can see that there's a list of recommendations being presented on the right-hand side of the screen. So we're going to focus on this type of recommendations, which is going to be a list. Okay, and so the importance of list is that it's not so each video by itself has some attributes of how relevant it is, but it also is present in a list. So the list overall composition of list also matters in terms of the recommendation quality, and therefore influencing users to click and therefore stay engaged with the platform. Here's a slightly different format, which is Netflix. So here, Netflix, you go from left to right, and so you have relevant movies and other content shown to you based on your preferences and what you've done before. So what's the concrete goal in today's talk? The concrete goal in today's talk is to recommend, as I said given the previous two examples, sequences of items. So for me, items for movies or videos over a period of time. So we want to give recommendations over a period of time. So maybe it's the same customer showing up every day, or it could be different customers, but they all are kind of interacting with our system over time. And when we recommend the sequences of items, we want to have this recommendation, the sequence to be as good as possible, which means in particular, we want it to be as competitive as possible to best in hindsight. So what does competitive to best in hindsight mean is that at the beginning of time, I don't know anything about my users, so I'm serving them some recommendations. Okay. Over time, I'm learning what these users' preferences are, and therefore I'm hopefully serving better and better recommendations. Okay. And so when I compare myself with how did I do overall, it should be as good as if I knew the user completely beforehand and gave the best recommendation in every interaction. Okay, so that's what I mean by competitive with respect to hindsight. And in particular, we're going to capture one key property. In fact, this talk is about trying to capture rich human behavior models. So we're going to capture a fatigue effect of the user. So users get drained out, if they see many recommendations and some of them are not relevant and so on. And the key contributions for at least this talk is that we develop two things. One is algorithms and also do some analysis. The algorithms we develop are behavior aligned, and the behavior is exactly fatigue behavior, both in terms of a single list of recommendations if the list is too long, or over time when people get worn out and desensitized. So both types of fatigue we capture, which is new. And also we come up with algorithms which kind of do well, which are competitive to best in hindsight, but also they come with what are called regret guarantees. And I'm going to tell you what regret guarantees are pretty soon. So this is actually a joint work with two of my students. One is Yunjun Wang, who's a student at JHU, and the other student is Priyanka Agrawal, who is a student at Urbana-Champaign. So there's a lot of related work in recommendation systems, of course, but also the underlying methodologies that we use for the personalization aspect. As I said, remember that personalization is a key facet or key theme in disruptive technologies that are coming into many business practices, all the way from insurance to content consumption to everything in between. So in terms of personalization, there is this rich line of work which looks at this closed loop feedback, where you get feedback from the users again and again. So that literature is called multi-armed bandits. It's an abstract problem, but it has a rich line of theoretical development that has been observed. Next, a set of related works is the combinatorial recommendations setting, where, as I said, a list of items is a combinatorial object. Combinatorial just means that there is an order relationship between items and there are multiple items being shown at the same time. And so in that case, the algorithms have to deal with really a lot of solutions, because if you have 5 items, there are 5 factorial ways of organizing them if you want to show all 5. And so there's an explosion in the number of choices that the algorithm has to make. Now, naturally, there's a mix of these both, which is called the combinatorial multi-unbanded slit topic, where there is some recent work on getting this user feedback over a period of every time over a sequence of interactions and improving your combinatorial recommendations. This work is also related to two separate lines of thread. One is called list fatigue and the other one is called time fatigue. And I'm going to explain what list fatigue is and time fatigue. And these are properties of what we think our users have. And so once we assume that the users get fatigued by recommendations if they're too long lists, or over time they get fatigued, then our algorithms have to design a recommendation such that they don't incur this, but they don't get fatigued. Of course, if you don't want them to get fatigued, you want to show highly relevant recommendations, of course. So there's two separate lines of work, and we'll also kind of improve actually on both the list fatigue research thread as well as the time fatigue research thread. In fact, in the latter, we come up with a very new model which is very realistic and give really good algorithms. So let me jump start and get to the list fatigue part. So each part, so both the list fatigue direction and the time fatigue direction will go in this way. First, I'm going to introduce how we think users behave in the recommendation system, in the sequence of interactions. And then given that behavioral model, we're going to design an algorithm which is as competitive with respect to hindsight as possible. Okay. So what do I mean by list fatigue? So let's say the platform is recommending a subsequence of items. So think of the YouTube example. So the platform in that snapshot recommended 4 videos. Okay. So let's say this boldface S represents that particular sequence. So there's an order relationship, and S subscript K just represents the item in the kth position. So S subscript 1, this is the item in the first position. Now let's start parameterizing our user. So we're going to introduce n plus 1 parameter. So where n is the number of items that we have. So maybe I have 1,000 movies in my catalog. So n is going to be 1,000. So for each movie, I'll have a number. Which is going to be U subscript J for a user. So for the rest of the talk, let's keep a single user type. So let's say the student population or the elderly population. And we'll talk about how to have different types of users later. So just think of it as a stochastic user who's parameterized by n numbers represented as U subscript J. And there's also, so this is the intrinsic preference of item J. So if if let's say when I'm supposed to recommend a sequence of items, I only show one item. So if I only show one item, even though I had the opportunity to show 4 videos, then that single item, because there's no list anymore, the single item's preference is captured by uSubscriptJ. So uSubscriptJ is some sense the probability that the user clicks on that item if it is shown, okay, in isolation. There's also one more parameter, which is Q, which captures the user's abandonment aspect to the abandonment probability, which just means that if the user is seeing a lot of irrelevant recommendations, they're just going to quit the platform, as in close YouTube or unsubscribe from a mailing list and so on. Okay. So these n+1 parameters together determine how the user is going to behave, and he's going to behave stochastically. So the way they're going to parse a given sequence is as follows. They'll start with the first item. They'll flip a coin with a bias U corresponding to the first item, whatever that number is. And if the coin lands heads, then they're going to pick that item and be satisfied. And so if that is the case, then the platform gets the revenue RJ for that item J. But if not, if the coin landed tails, then they either quit the system, they abandon with probability Q, or they move on to the next item in the list and repeat the process. Okay, and so what we know is some costs and benefits, which is R sub script J are the benefits of if the user picks up one of the items in the list, and C is the cost if the user completely abandons the system. Okay. And so they linearly parse the list from top to bottom or left to right in whichever interface you're thinking of, like YouTube or Netflix. So now let's think about what is the best thing we could do if we know everything about the user. By everything about the user, I mean that we know UJs and Q. Okay, so that if we know UJs and Q, we can actually compute what some summarizing quantities. The first quantity is the probability of selecting item A given a sequence boldface S. Okay, so that probability I can compute given U's and Q's, U's and Q. And similarly, I can also compute the probability of abandoning the platform given this boldface as sequence of items. Okay, so given these two numbers essentially, but pi of s is for each item as well in the list. So once we get these numbers, we can actually compute we can write down an optimization problem whose objective is what I'm calling as the expected utility for the firm. Okay, which is just a linear combination of these probabilities of clicking or selecting an item and probability of abandonment. Okay, if they pick an item I get a revenue Ri, and if they abandon the system, I lose with a cost of C. Okay, so it's just a linear combination of that, and that's the objective. It's the expected utility. And I want to, as a firm, I want to now, if the user is characterized by these UJs and Q, which I'm just representing as boldface U and Q, then I need to find that sequence, that is the boldface S, which maximizes this expected utility for me, okay, because I'm getting a revenue R and sometimes losing with a cost C every time I change my sequence of items, okay. So this is the optimization problem if the user is known, which is the U and Q is known. It is and you will have business constraints relating to, okay, some items should not be shown together, maybe, and so on. And so this is an optimization problem. It could be hard in itself, very difficult in itself. But what we are interested in is in the following sense. We are interested in personalization. So at the beginning of time, we don't know anything about the user. We don't know U and Q at all. But over a period of time, maybe over 100 interactions, we should learn U and Q well enough so as to be recommending the best sequence S as much as possible. Okay. And so what we'll see, and this is more of a technical detail, is that direct application of existing algorithms which have been developed for this type of personalization, as I said, I showed in the related work, they are suboptimal. And let me tell you what suboptimal is. So this is a little bit of a math heavy slide, but the point of the slide is to show the guarantee first and then the intuition of the algorithm next will follow. So the guarantee of our algorithm, which we call SBORS, is as follows. So it's a guarantee on what is called a regret, which is how competitive I am with respect to hindsight. That is captured by the left-hand side term rig, where capital T denotes the time horizon, so the number of interactions I'm going to have with the user. And the user is characterized by U and Q. So with this user, if I interact with capital T number of rounds, I'll have what is called an expected regret of my algorithm SBORS, and it's going to be, so the right hand is just saying that it's going to be small. Okay. The important thing is the left-hand side is what is called a cumulative regret. So as t increases, your cumulative regret, since it's a cumulative term, it has to increase. But as right hand side is showing us, and the t, it doesn't depend. too badly on t. It's sublinear in t, which means that it's, for example, depends on square root of t. It grows as square root of t or square root t log t, and so on. Okay, so which is nice. Okay, anything which is less than t is actually good, which symbolizes that the algorithm is learning. Okay, it's learning while earning, making good recommendations. Now, what is the regret objective itself? You can see the regret objective at the bottom. It is the comparison of what you would have done if you knew the user beforehand. So that's the first term here. So if you knew the user beforehand, then you'd compute you would solve the optimization problem that I showed in the previous slide. Let's say the solution is S star, then you would keep showing S star in every of those t interactions, and you'd get some expected utility. That will be the highest number that you could achieve. And but if you don't know the user beforehand, you would show a sequence of items in every round. So that is superscripted by little t here. And so you'll keep changing that recommendation list, but hopefully towards, maybe after a few rounds, you start converging to the list that is as good as S star, as in maybe it is equal to S star and so on. Okay. So that's the regret guarantee. And let me now focus a little bit more on the algorithm. The algorithm is what is called is based on a very popular technique called Thompson sampling. So this is a very intuitive algorithm. It's a Bayesian algorithm where what it does is it maintains, since I do not know the user, let me maintain a belief on what the user could be. So for example, if the user was supposed to have some U and Q, but I don't know what they are, so let me maintain some sort of a Gaussian distribution or some sort of a beta distribution, for example, on each of the parameters that I don't know. Okay, and so that would be my belief. The algorithm is saying, okay, if that's your belief, let me sample from that. Hopefully, regions where your belief is high, maybe those samples come out. And based on that sample, I'm going to solve the optimization problem that I showed in the 2 slides ago. If I solve the optimization problem, I'll get a particular sequence to be shown to the user. I'll actually show that sequence. And the user is going to interact with that sequence. Maybe they'll abandon, maybe they'll take an item. And using that, now I know what the user did for that particular sequence. I'm going to use it to improve my posterior distribution. And how would I improve it? Just by Bayes rule. Okay, so that's how the algorithm works. So that's how the feedback loop works. So, but it's an old algorithm template. For some information about the feedback, you can see that you can have feedbacks. You can maintain what I call, you can maintain summary statistics at the end of each round of interaction. So Ci of t, for example, could be the total number of users who ended up selecting item I so far whenever it was shown. Okay. So given the summary statistics and some additional summary statistics, you can actually maintain parameters of the posterior distribution. So ideally, you want to maintain a posterior distribution which is not too complicated. So you could probably choose a parametric family and hope that there is some conjugacy that works out, conjugate prior idea that works out. And so you can just maintain some summary statistics and parameterize your posterior distribution. So in Thompson sampling, the original algorithm, for this type of setting, people used to maintain beta distribution. But what we are going to do, beta distribution for the parameters u and q, because these are numbers between 0 and 1, so they are bounded, an unknown quantity. So our belief can be also bounded between 0 and 1. But what we're going to do instead is, we're going to maintain Gaussians. So Gaussians have a support from -∞ to infinity, but model of that issue, the summary statistics that I showed in the previous slide can be used to compute the means and variances of the parameters of my distribution. So I'm going to think of a multidimensional Gaussian distribution, so one per item, and one more for the Q term. The abandonment parameter, and so I will have so many Gaussians, and I just need to maintain their means and variances. Another trick that I'll not get into too much detail is that I'm going to also correlate when I'm going to sample from this belief that I'm maintaining. So when I want to sample from the belief, if it's a bunch of Gaussians, I can draw independently from each of the Gaussians. Instead of that, I'm going to somehow correlate the samples that I get. So instead of drawing from, let's say, n+1 independent Gaussian distributions, univariate Gaussian distributions, I'm going to sample from maybe a 10-dimensional Gaussian distributions, and then somehow generate, transform these original samples to get these n+1 realizations. Okay, so that's what's written here. I will not get into the detail of that, but with that, those changes, assuming doing Gaussian approximation and doing some correlation, we can actually get a really good performance. And so, what is this plot? These 4 plots showing? Let's just focus on the top left. Okay, on the x-axis this is the number of interactions. So you can see that there's already 100,000 interactions. But you can imagine that for web scale, e-commerce type of situations, digital solutions, actually, the number of interactions is not too large, especially you're thinking of a user type like student population and so on. You can see regret, which is cumulative regret, and it has to grow. But it has to grow with respect to the number of interactions, but it's not growing too much. Ideally, it should flatten. If it flattens, that means you've really learned the best sequence of recommendations you are supposed to show for this user or user type. Okay, and you can see that as I change the, I kind of have more varying utility values for each of the items. Regret can vary quite a bit. So that's is just showing a variation with respect to how the underlying utilities of the items are. But what we want to capture is the pattern. Okay, so the regret is going sublinearly. So the algorithm actually works. And additionally, I have a few more plots on very similar regret versus number of interactions, where I change a few other things. For example, as I said, from the summary statistics of interactions with the users, I have to somehow parameterize my Gaussians. So those estimators, they have parameters themselves. So I'm changing those parameters here. For example, they're called alpha and beta. If I change them, I get a certain type of variation with respect to how the regret varies. Okay. So what is the intuition for the regret bound? Why does the algorithm work? Okay, so the way to understand it is to write the regret as a function of two terms. You can decompose it in two terms, the first term and the second term, where what I've done is just add and subtract this blue quantity. So if you ignore the blue quantity, if you sum these two, what you end up on the right hand side is just the definition of regret, which I showed a few slides ago. Okay, now I have added to the blue term, which is the common, which is sorry, I've added the black term, which is common, added and subtracted the black term. Now for the first term and second term, I'm gonna bound them separately. I bound them as a function of hopefully a sublinear function of p, hopefully a polynomial function of the number of items, and so on. Okay? So the first term can be bounded if first term can be bounded if what happens is, because of correlation, at least one of the our samples that I sample in the correlated sampling part leads to what is called an optimistic round. What is an optimistic round? An optimistic round is where the performance of S star on the sampled U1Q that in that round that I use to optimize, the performance of a star for that U prime and Q prime that I sampled is greater than how a star would have performed with the true U and Q. Okay, so these are the parameters are changing, U prime and Q prime and U and Q. A star is a fixed sequence of recommendations, and we're just saying that this inequality holds, and that's an optimistic round. And what happens is by choosing an appropriate R, you can get many optimistic rounds, and that leads to the first regret term being small. Okay, the first regret term being small. Similarly, the second term is small if the difference between the objective values parameterized by samples and the true parameter for ST is small. So, sorry, you can see that ST, now the solution is again fixed, but now you have the parameters which are changed, U prime, Q prime, and U and Q. And this, we are comparing two objective functions of two different optimization problems at different parameterizations for the same solution. And we can actually show that the second term is also small if the objective function structure, which is whether it's, in particular, we are going to look at monotonicity and Lipschitz properties, if they are nice enough. Okay, and we actually see that it is nice enough for this optimization, our problem. And so that's why our algorithm gets low regret. Okay, so let me move on to the next part, which is temporal fatigue. So here, remember, we were interacting with users in the previous case, but there was no dependence on one interaction with respect to the other. So maybe I interact with you and show a list of recommendations. You don't like it, and so next time when I show a bunch of recommendations, you don't remember what I showed before. Okay, so there is as good as saying the user doesn't remember what happened previously. But in temporal fatigue, which just means that I'm going to capture users as having fatigue over time, so they're going to interact with my system again and again, and they will, if they've seen irrelevant things before, then they will not like it. Okay, and let me tell you exactly what the model is for capturing temporal fatigue. So for this part, I don't really need a notion of a list. So let's say we have some objects that we want to show. It could be a list, it could be a single item. So let's say we want to show capital K items. Okay, and each item has an associated reward, okay, which is the if I show this item, the person, the user is going to flip a coin with some bias related to the item, and that's going to realize, for example, a buy or a no buy, or watch it or not watch it, and that random variable is R, okay. But there's also going to be two more random variables if I show a particular item, okay, in a particular round t, little t, and those random variables are dtj and ztj, okay. And I'll tell you how those capture temporal fatigue in next slide. The mean of R is going to be mu, so these are the mean rewards. So if I knew everything about the user, which is these mu's, then you would show the item with the highest mean reward. But we don't know everything about the user. In particular, we don't know mu's. But let's say we know expectation of D and expectation of Z. I've dropped J for simplicity in this talk, but we know these expected values, but we don't know the realizations of random variables themselves. Okay. And let's say JT is the item that we're showing in at time T. Now, what do these random variables do is as follows. They capture the user behavior in the following way. So the platform observes the reward R if item J was shown at least DTJ number of times and at most ZTJ number of times in the n most recent time steps. So the user is going to say, oh, you showed me item J. Now let me look back and see what all items you showed. If item J, among all the items that you showed in the previous n rounds, if item J was shown at least DTJ number of times and at most ZTJ number of times, then I'm going to give you a reward which I picked just now, it is RTJ. If not, I'm not going to give you any reward. Okay, so that is captured by this mathematical expression in the center, but intuitively what it's trying to say is that think of me seeing an ad for Coca-Cola. So let's say at time t. So let's say I've seen a bunch of 100 ads before, and right now I see an ad for Coca-Cola. So let's say right now I realize three random variables. I'll buy Coca-Cola, so that's RTJ. Let's say it's 1. And there's a DTJ and ZTJ. Let's say they're 3 and 10. It just means that if I've seen an ad for Coca-Cola now, I'm going to buy it if I've seen the same ad at least 3 number of times and at most 10 number of times in the previous 100 ads that I've seen. Okay, and if that is the case, I'm going to give you I'm going to actually buy it. If not, I will not. Okay, and so what is it capturing? It's capturing the wear-in and wear-out effects of the user. So wear-in and wear-out effects constitute what is called a priming effect in advertising, where you want to repeat the ads just enough so that people remember and therefore do a call to action, but you should not repeat an ad too much such that people get desensitized to the ad. Okay, so this is a certain way of personalization because you're trying to capture a particular user behavior that is being exhibited in the advertising in this advertising setting. Okay, so here is a pictorial diagram. It's just showing that at different x-axis is showing x-axis is showing times, and y-axis is just showing the window of number of repeats that you could have done. So, for example, here for example, the last column towards the right of this plot, you can see that if you have repeated at least one number of times, but at most, maybe 5 number of times, then you would get a reward. Okay, so given this temporal correlation, existing multi-armed binary algorithms fail quite badly. And to illustrate that, here is a diagram. Here, which is trying to show that if you just blindly apply an existing multi-armed binary algorithm, depending on the mean rewards, remember the mu-j's, which are mean rewards of each of the arms or each of the items or each of the ads. So depending on their values, the mean values, the number of times you change between arms is quite frequent. For example, if you look at the red curve, it is in a situation where the mean rewards of about 7 of the arms are almost close to each other, or there are 7 arms out of here 30 arms which have almost the same mean reward and they're all high. Okay, so those are, I'm just calling the optimal arms. If that is the case, then each arm is being repeated is actually quite low in a 15 interaction window. So if you look at any chunk of 15 interactions, if an arm at the end of the 15th interaction, if you're playing the first arm, the probability that you're playing the same arm in the previous 15 rounds is quite low. Okay, so all these algorithms have this issue, so therefore they cannot overcome the wear-in effect, and so you will lose almost all rewards, and therefore your learning is completely derailed. So we really need a new algorithms. And so here is our algorithm. In fact, we have two algorithms. One is capturing just the wear-in effect, and the more general algorithm is capturing both the wear-in and the wear-out effects. Okay, and here we show the list. The first 3 rows are showing existing algorithms to get a sense of how do these algorithms perform in terms of guarantees. So the guarantee, if you look at the column on the right, you see that the dependence on the number of arms is under square root, which is k, and it is also sublinear in T. So this is the same thing that we saw several slides ago when we had list fatigue. So we prefer algorithms which have sublinear in T dependence. Okay, and you can see that the last three rows of this table show our algorithms. So when there is no priming effect, we do as good as previous algorithms. But when there is priming effect, which is the wear-in effect, we have an additive term. And when there is both wear-in and wear-out effect, we have an additive term as well. But the dependence on the number of arms slightly increases. Okay, and but still, the algorithm has guarantees even in this temporal, dependence setting. Now, what does the algorithm itself look like? The algorithm actually works in phases. Remember, we're going to interact with the user again and again. I mean, this is a stochastic user, so it's not the same deterministic user. So we interact with them, but we're gonna bunch these interactions into what are called phases. So in each phase, think of in each phase we're gonna have several interactions. And each interaction is we're gonna display an ad, and they're gonna do something. They'll buy or not buy, for example. Now in a phase we're gonna have phase, in individual successive runs of each of the ad, which just means that we're going to play each ad successively for a few times, switch to another ad, play it successively for a few times, and so on, and bunch them together to form a single phase. Okay, and then at the end of the phase, we're going to now say that, oh, we played these arms a few number of times. What were their mean rewards? If the estimated mean rewards are too small, we're going to drop those arms and then prune our list of relevant ads for this user and keep going. Okay, so this is a phase-based strategy, and we're going to rely on it. But a very important part of this algorithm is to determine how many times you're going to repeat, because if you repeat too many times, you're going to do badly um, uh, because of wear out. And if you don't repeat too many times, you're going to have wear in effects. So, uh, and that's what I'm trying to show in this slide, where I'm trying to say that if DTJ, which is the wear in effect, is bigger than the number of times you're repeating, you don't collect any reward. But if you can't repeat the same arm too many times because it is suboptimal, so you're wasting number of rounds, and so your regret will be high. Okay, so the choice of the phase length for each of the arms and the overall phase is kind of critical, and that's what we get the right choice so as to give our algorithm an algorithmic guarantee. A theoretical guarantee. And you can see empirically also it performs well. So the blue curve with a yellow band is our WI-UCB algorithm, which actually has a lower regret, cumulative regret compared to other algorithms. All the other algorithms have linear regret in this example. X-axis is representing the number of interactions, and y-axis is representing cumulative regret. In the next slide, we are just showing the dependence with respect to how much wear in effect influences regret. For example, if you're going from the blue curve, which has a very limited wear in effect, to the black curve, which has a very high amount of wear in effect, you can see that the cumulative regret increases. This is with respect to our own algorithm. And so this is how wear in effect influences regret or the performance of your algorithm. Okay. The next is the more general setting where we are considering both wear in and wear out. So remember, in wear in, it's just that if you can just prime the user enough, then they're gonna purchase your make an action. And let's say there is no wear out, then you can keep on continuing showing the same ad again and again and again and reap rewards. Okay, but that's unrealistic. So you want to have wear out. But the moment you introduce wear out, it's not clear what is the best thing to do, even if you know everything about the user. So let's say you know the mean rewards of the arms. You also know the wear in and wear out effect, mean values of the random variables. It's still not clear what is the best set of arms. What is the best thing to do in each round. Okay. So what we do is justify why a choice such as the following, where you pick the top two arms. So let's say we have full information in the sense we know everything about the arms and so on. Then pick the top two arms with respect to their mean rewards and keep switching them. Okay, so that's what we're saying is we're trying to justify that we justify in our paper that that's a good enough strategy, which is you figure out the top two arms and switch between them. Switching between them allows you to take care of the wear out effect, and playing them consecutively takes care of the wear in effect, and so you really reap a lot of reward, and so you're going to be really good. So with respect to that benchmark, now we're going to design an algorithm which doesn't know anything about the user a priori, but is able to match this benchmark. And to do so, we introduce a new idea, which is the idea of compound arms. So remember, in the first part, we were working in phases, where a phase was just a chunk of repeated plays of different arms or different items or ads. So what we're going to do is now, because our benchmark included the choice of switching between top two arms alternatively, we're going to think in terms of pairs of arms. So let's say we had 3 arms, then we're going to think of 6 pairs, all possible pairs here. And then each of the 6 pairs we're going to think of as a new problem. So each of the 6 pairs, now we have 6 meta arms or compound arms. And again, we're going to apply the same type of algorithm that we applied in the first setting where we only had wear-in effect. Because now with the compound arm, whenever we have to play a compound arm, we're going to play them one after the, we're going to play them um, um, uh, we're going to play them with equal probability in each. When a compound arm has to be played, there are 2 arms in the compound arm, so each arm is played with equal probability. So in one round I may play the first arm, and the second round I may play the second arm, or even the first arm with some probability. So it's equal probability. So with this strategy, we actually can counter both the wear-out effect as well as retain the way we were countering the wear-in effect. And so this strategy works. And again, there's a calculation on how long the phase should be, because if it's too long, then you're going to waste interactions and not get high rewards, and so you're going to be bad in terms of regret. So we do that. And here in this slide, we're trying to show empirically that algorithm works. So in fact, it works where the previous algorithm, which was only catering to the wear-in effect, fails. So you can see almost all algorithms fail, have linear cumulative regret. So y-axis is cumulative regret, and again, x-axis is the number of interactions. You can see that the green curve, which is the wear-in, wear-out UCB that we have developed, is performing better. Okay, it seems to have sublinear regret. So with that, let me recap and summarize what all we have discussed so far. So the way I motivated this problem is that I motivated the talk was to say that personalization is a big disruptive change that is happening with digital businesses, especially businesses like e-commerce, advertising, and recommendation systems, which permeate many different services in the digital world. And so a key aspect of personalization is this aspect of trying to take feedback over time through interactions and improve your offerings in subsequent interactions, improve your actions, which could be recommendations or ads. Okay, and so there's a huge need for behavior aligned algorithms. In particular, we talked about recommendation systems. Now, how do you align your algorithms to behavior? One way which we have approached here is to capture the rich behavior that the user exhibits. For example, in the first part, we looked at user exhibiting a list fatigue behavior, where if the list has their more relevant item is at the bottom of the list, maybe they're gonna abandon your app, or not click on the most relevant item. Similarly, in the second part, we were looking at temporal fatigue, where there is wear in and wear out type of effects, where if the ad is not shown enough number of times, then the people don't remember. But if it's shown too many times, people get desensitized. So you want to show the right number of times. You want to repeat the ad just the right number of times in recent past. Okay, so those are 2 behaviors that we captured. And we addressed how to learn the parameters. So both these models of user behavior, where they had when they were interacting with a list and when they were interacting with items over time, we had parametric models. So there were parameters like the mean rewards, the and the wear-in wear-out effect mean values, or in the first part there were these mean intrinsic utilities of the items, and an abandonment probability, and so on. So all these parameters we were supposed to learn, but we are doing way beyond that. We are not just learning the parameters, but at the same time also ensuring that the regret is not low, which is that we are doing both the statistical estimation of the parameters just enough so that we can do as best with respect to our offerings compared to as if we knew the user in hindsight, as in we knew the user from the first step onwards. Okay, so we are really learning while earning. And so these parameters, our algorithms also come with regret guarantees, which is a very nice feature to have in these settings. A lot of directions which are yet to be explored. As I said, personalization is not a solved problem because, for example, today you can see there are several drawbacks or several issues with the type of personalization systems that you see. So a lot of scope for improvement. For example, I have not considered fatigue across time as well as within a list simultaneously, because that would make a much more difficult user behavior model for which to give a guarantee, an algorithm with a guarantee. We have not also used context, by which I mean that in most of the discussion today, I was talking about the same user, same stochastic user, in the sense they had the same parameters U and Q in the first part, and in the second part, the same mean reward, for example. Now you can think of context which parameterize 2 students in the student population. So if I am a student and I'm an engineering student versus a um, um, a math student, I would have maybe a different viewing pattern of my online courses on YouTube or something. Then I want to recommend based on those previous interactions. Then they would have different contexts, and so there's a way to tame statistical complexity when contexts come into the picture, and it kind of relies on supervised learning ideas. And the last part is capturing multiple behavior models simultaneously, multiple behavior patterns simultaneously. It's not just fatigue aspects. There are other aspects to users. Users may have different types of preferences. Users may have different types of sensitivities, constraints, and interests. So being able to capture your offerings to the behavior that is exhibited, rich behavior that is exhibited by consumers, really can push forward, the impact of your offerings. So these are some things that can be done in the future. But in general, personalization is a key, I guess, pillar in this disruption that AI is causing in businesses in general and digital business in particular. And hopefully this talk gave you a sense of the technical underpinnings for personalization in a sequential interactive environment. Thank you so much for listening.